Let's take a look at one more example. A machine produces metal rods used in an automobile suspension system. A random sample of 15 rods is selected, and for each of those in the sample, the diameter in millimeters is measured. Some amount of variability is acceptable. Variability that's too great results in unstable rods. Variability that's too small is probably taking too long to machine to exact specifications. As a quality control engineer, you might want to know whether or not the standard deviation is 0.02 millimeters. Let's draw conclusions with 95% confidence. Okay? So we want to know something about the variability of this machining process, and the variability can't be too great or it can't be too small. Too great is a bad situation. Too small, it's taking too long to get things really exact. We can accept some amount of variability. Okay? So we've got an equality kind of statement about our variability. So is it equal to some value? Is it equal to a standard deviation of 0.02? So the variability would be 0.02 squared, or variance would be 0.02 squared. Or is it not equal to 0.02 squared? Okay. We go and collect a sample of size 12, and we find that the sample standard deviation is 0.0253. Therefore, the variance would be 0.0253 squared. Okay? And we want to draw conclusions with 95% confidence. So let's take a look at this chi-square test statistic. It would be n minus 1 times s squared over the hypothesized value, sigma naught squared. Okay? That is 12 minus 1 times s squared, which is 0.0253 squared, divided by the hypothesized value, 0.02 squared. Okay? If we work this out, just arithmetic, we get a test statistic of 17.6. Okay? Critical value approach. Let's do that one first. Okay, we've got a chi-square axis with degrees of freedom 11. So here is our distribution for the chi-square test statistic. And this is a two-tailed test. So we want 0.025 up here, and we want alpha over 2, 0.025 down here. Okay? This chi-square 0.025, degrees of freedom 11. If we go look that up in the table, very straightforward to find. Go down to the degrees of freedom 11 row, over to the 0.025 in the upper tail column, and we get 21.92. Okay? For this value down here, we want 0.025 in the lower tail, but the chi-square table always gives us the upper tail. So we want chi-square of 0.975 in the upper tail. Okay, go down to the 11 degrees of freedom 11 row, over to the 0.975 column, and we get a value of 3.81575. So we've got our critical values, we've got our test statistic. Our test statistic lies right about there. Okay? It lies in the non-rejection region. So we don't reject the null with 95% confidence, and we conclude that the variability is just right. It's not too big, it's not too small, it's right where we want it to be. Okay? So we don't reject the null with 95% confidence. Okay? Now let's say we want to use the p-value approach instead. So with the p-value approach, as always, we plot the test statistic directly, and we find the area in the smaller tail, multiply that area by 2, and that gives us the p-value. Okay? So we go see what we have in the book. And what we have in the book would be this tail. Okay, so this is chi-square degrees of freedom 11. We have this. We have 17.2750. If you go look in the chi-square table down to row 11, row degrees of freedom 11, you'll find this value hanging out in there associated with an upper tail value of 0.1. Okay? But that's not this exactly. So let's see what else we have. Okay, go back to the table, the degrees of freedom 11 row, and we find this. we find this value on the axis, 19.6751. That area is 0.05. Okay? So this value and this value on the chi-square axis bound this thing. Okay? Bounds this value right here. So that must mean that this p-value, or well, this is just an area first. We have a two-tailed test. So this is just the area above the test statistic. That area must be bounded by 0.05 and 0.1. Okay? We don't know what it is exactly, but it's bounded by these two values. Okay? So the area above the test statistic is bounded by 0.05 and 0.1. Okay? We've got a two-tailed test. That means that we multiply that area above the test statistic by 2 to get the p-value. So the area by 2 gives us the p-value. That would be this times 2, 0.1, this times 2, 0.2. Okay? So our p-value associated with this test statistic lies somewhere between, but we don't know exactly where, 0.1 and 0.2. Okay? That's a pretty big range, and the lower bound is bigger than our value of alpha. Okay? Lower bound bigger than our value of alpha, and really it's bigger than any kind of convincing p-value that we would ever choose. P-value greater than alpha. Therefore, we do not reject the null hypothesis. Okay? We only reject the null if the p-value is less than alpha. Here, it's not. Okay? P-value quite large. We're not in any way compelled to reject the null with 95% confidence. Okay? But here we have to bound the value. Let's say we wanted that p-value exactly, just because we're stats nerds and we just want to know exactly what that thing is. So let's use Excel. Okay, we can use the chi-square .dist function in Excel. Okay, it wants the value on the axis here. It wants the degrees of freedom, and it wants whether or not this distribution is cumulative. Okay, so let's just say we want the cumulative distribution. That will give us all of this area up to that value. So let's read in 17.6, comma, degrees of freedom 11, comma, true. Okay, so if we implement this equation in Excel, we should get something that looks like this, 0.9087. Okay, that's the cumulative area. We say cumulative true. That's the cumulative area between the lower bound 0 up to the value on this axis, 17.6. Okay, but that's not the area we want. We want this upper tail area. Okay, that upper tail area would be the complement of this, 1 minus 0.9087. So the area is 1 minus 0.9087, which is 0.0913. Okay, so that just gives us the area. Remember, for a p-value calculation, when we have a two-tailed test, we got to find the area, multiply it by 2. Okay, so the p-value in this case is this area, 0.0913, multiplied by 2, and that is 0.1826. Okay, 0.1826, big p-value, way bigger than alpha of 0.05. Don't reject the null. Note here, 0.1826 is in between these two bounds that we found earlier. If that didn't happen, then we did something wrong somewhere. Okay, and if we didn't draw the same conclusion that we did over here, then we did something wrong. I should also point out that, yes, so if we would have just said this area, so if we're unsure which area to multiply by 2, okay, do we take the upper tail or the lower tail? Okay, the way to figure this out is if we had taken this area, which was 0.9087, and we multiplied that by 2 to get our p-value, multiplying that by 2 gives us a value of 1.8 something, okay? That we can't have a probability. A p-value is a probability. Can't have a probability of something greater than 1. So this area is the one we needed to find, and that was 0.0913. When you multiply that by 2, you get something reasonable that sounds like it would be a p-value. Sounds like it would be a probability, okay? So here, p-value 0.1826. It lies between 0.1, 0.2. We could use Excel. We could use the book. For the p-value approach, we could use the critical value approach, and still we come up with the same conclusion about the set of hypotheses dealing with population variances.